So it's brought to my attention that I missed going back to this page. Now, the problems that you do are these problems, okay? But I'll do one more example, sort of lay it out. But this, how I did these problems, or how you do titration problems in general. But I didn't get a chance to go back and show you what all the different things were. So what I was able to do this semester was actually record my wife doing some of these things. And so I'm going to show you those video clips that we created actually for the Chem 1A class. But I'll be able to talk about what each of these items are. So it's brought to my attention that I missed going back to this page. Now, the problems that you do are these problems, okay? But I'll do one more example, sort of lay it out. But this, how I did these problems, or how you do titration problems in general. But I didn't get a chance to go back and show you what all the different things were. So what I was able to do this semester was actually record my wife doing some of these things. And so I'm going to show you those video clips that we created actually for the Chem 1A class. But I'll be able to talk about what each of these items are. All right, so let's go over what some of these different things are, okay? So the burette is that long glass item like this, right? And it has a point on it, and it has like what we call the stopcock here. That's for turning it on and off. And then you have a liquid in here, and this is the titrant. Okay. The titrant is what you're going to be used to titrate. This is the term titration. The analyte or the titran. So the analyte was what was in the Erlenmeyer flask. Now, this in our case was oxalic acid. And this is sodium hydroxide. And you'll notice that when you do titrations, and it doesn't have to be exactly like this, but you have sodium hydroxide in the burette, and you have an acid in the Erlenmeyer flask. These always have to be a combination of an acid in one and a base in the other. So in this case, we have the base here, and the acid is over here. And the reaction that actually takes place is this one. Oh, sorry, oxalic acid. Oh, this is, sorry, that's C2O4, and then C2O4 plus H2O, and there's two of those there, okay? So what's happening is the sodium hydroxide is being added, and it's being used to neutralize the oxalic acid. Now, initially, you have oxalic acid in here, and when you add the sodium hydroxide to it, it begins to use up the oxalic acid. But since you're adding the sodium hydroxide to the Erlenmeyer flask, right, the oxalic acid is in excess, and so the sodium hydroxide is what actually gets completely used up at the beginning of the titration. But the whole time you're doing this is also being used up a little bit at a time as you're adding the titrant. This is where the phenolphthalein comes in. The phenolphthalein is, I'm just going to call it P, right, is colorless with excess acid, and then immediately turns pink, and the color is actually fuchsia. And the fuchsia is that bright, like neon pink color, right, with excess base. So as soon as it turns pink, you know you've used up all the acid. And then what we do is we use the molarity information for the sodium hydroxide and then the volume that's dispensed to tell what the moles of the acid are that we neutralized in this reaction. Okay, so let's go back and let's pull up the numbers that we got from the burette for the titrant. Okay, so we had an initial volume and we had a final volume. And again, we said that initial volume is about 6.75. It might be 6.76. It depends on how good your eyes are and stuff like that. A little bit. And then we said that final volume is what? Right? Well, I said in my notes or in my head, I said that looks like it's 24.01 probably. So I'm going to call that 24.01. And the units on the burette are milliliters, okay? So my net volume, that's how much titrant got dispensed, okay, is V final minus V initial. That's how you use the burette readings. So where you started from is V initial, where you ended at is V final. Then we can say that this is 24.01 milliliters minus 6.75 milliliters. Always, always, always go all the way out to the 100th of a milliliter on a titration calculation. There's almost never a reason not to, okay? And this will give you more significant figures if you keep track of it. Okay, so we'll do the subtraction. And, you know, I'm not going to trust myself because I'll make a mistake when I'm making a video for sure. 24.01 minus 6.75. I almost made a mistake there, huh? 17.26 milliliters. So that's the volume. So like in a problem where we talk about a titration problem, right? We say it took 32.05 milliliters of sodium hydroxide. Well, this is how that number is gotten. You make an initial measurement and a final measurement, and you subtract. Okay. We usually try not to start at zero because if we think we're at zero, we tend to bias our thoughts in reading it as zero, when often it's not. So we typically try to avoid starting at zero to force ourselves to measure it before we start. So here's our example. We're just going to use the data that we just took off the video. But let's say it takes 17.26 milliliters of sodium hydroxide to titrate. And the sample mass that was used with this titration was 0.1097. So 0.1097 grams of oxalic acid. Calculate the NaOH molarity. Now, it said in the video, if you remember right, it said it was 0.1, but it was only one significant figure because when you make sodium hydroxide, it's really hard to tell exactly what the concentration is. So that solution was prepared by somebody else and then given to you, right, in this example, and then you're titrating it to figure out exactly how close they made it to the 0.1 molar. So what do we do when we solve these problems, right? You start with whatever that allows you to calculate the moles of sample, okay? Now, the way you get moles from a volume is you need to know the molarity, so that's not it. But you can always get moles from grams. So what we're going to do is we're going to take the grams of oxalic acid, I'm just going to call it OA, and we're going to convert it into moles of oxalic acid. And then what we're going to do is we'll use the chemical reaction that goes with this titration, which is this one that I wrote up here. And we're going to calculate the moles of sodium hydroxide that were, or sorry, the moles of oxalic acid that were reacted with the sodium hydroxide. So then what we're going to be doing is converting this to moles of NaOH. So now here's what you have to do next, or maybe you do this first, because these things don't have to be done in a particular order. But they're asking you to calculate the molarity of the sodium hydroxide. So sodium hydroxide molarity is defined as, or molarity of anything is defined as moles over liters. Well, if I want moles of sodium hydroxide per liter of sodium hydroxide, right? Those are the two things that I need to find. This is how I'm getting my moles of sodium hydroxide. And this is the number, although it's not in liters, that's the number that will give me the liters of sodium hydroxide. So let's go ahead and do this calculation first, and then we'll go ahead and convert this to liters, and we'll plug it all into here and get the molarity of the sodium hydroxide. So to do the first conversion, right, I'm going to have 0.1097 grams of oxalic acid. And then what do I need, right? I need the molar mass of oxalic acid. Now, one of the things it doesn't say in here is it's actually oxalic acid dihydrate. So its actual formula is H2C2O4.2H2O. And I get that having a molar mass of 126.07 grams per mole. So I'll go like this, 126.7 grams of oxalic acid for every 1 mole of oxalic acid. And then when I'm looking at this formula, it says that there are 2 moles of sodium hydroxide for every 1 mole of oxalic acid. So I'll finish this as 2 moles of NaOH for every 1 mole of oxalic acid. So we're going to calculate that value. I'll pull up a calculator to do it actually. It's going to be 0.1097 divided by 126.07. I left the 0 out there, times 2. And that comes out to 1.740 times 10 to the minus third. Right, 1.7403 times 10 to the minus third moles of NaOH. And again, I left out a 0 here. That's actually the actual molar mass. I don't know why I didn't write it. I just didn't. Anyways, now we're going to calculate, convert this to liters. Okay, so I have 17.26 milliliters times, and depending on how you learned how to do it again, 10 to the minus third liters per liter. Right, that just ends up being 1.726 times 10 to the minus 2 liters, like that. All right, so I can plug those in to here. 1.743403. I have something as zeros today. 03 times 10 to the minus third moles of sodium hydroxide divided by 1.726 times 10 to the minus 2 liters, like that. So pull up my handy dandy calculator. And I'm going to divide that by 1.726 times 10 to the negative 2.